Okay, let's start today's topic. We will first introduce current sense. Current sense in the market is being used by more and more customers. Initially, it was mainly used in 5G base stations and automotive markets, including industrial applications and server markets. Gradually, there has been a demand for current sense amplifiers. The market size is quite large, according to market research. It is expected that by 2025, it will reach over 60 billion NTD with an annual growth rate of 10%. At the moment, we see that the market includes automotive, networking, industrial, and even defense sector-related applications. Recently, we also see an increasing demand for current sense because of the issues related to carbon credits. Some consumer system manufacturers are also focusing on detecting total power and total energy consumption and reporting this data to brand owners for data collection. Basically, they also use a digital current sense for detection and reporting. As I mentioned earlier, there are many applications, and customers may use it in different ways. The main applications of current sense are for protection and for carbon credits to monitor power, voltage, and current. For motor-related applications, it may be used for loop control and for protection. For example, in power delivery applications, there is a function called second OCP, which is overcurrent protection, in PD applications. It may need a power IC with an external sense resistor. The sense resistor needs to pass safety regulations. For single-fault applications, it requires high current and needs to pass safety regulations. The probability of passing is relatively low. Therefore, most customers add an additional current sense at the output, whether for the second OCP or for all single-core testing to pass under these conditions. For monitoring, as I mentioned earlier regarding carbon credits, customers may need to report the total power consumption. Additionally, in server applications, it may be used to detect different power rails, vCore, GPU, PCIe fan, etc., to optimize the system. These are the common application scenarios for current monitors. The composition of a current monitor is essentially an OP, which includes an amplifier with a gain and an external sense resistor. Simply put, the output is the sense current multiplied by the resistor. The voltage across the resistor multiplied by the gain is the output. So, essentially, it consists of these two components, the resistor and the op. The voltage across the resistor multiplied by the gain is the output. So basically, it consists of these two components, the resistor and the op. It is a type of op, but with a built-in gain, which eliminates the need for external components and reduces error. Next, let's introduce the types of current sense amplifiers. Currently, in the market, we commonly see analog and digital types. The main difference between these two is that analog amplifiers have a faster response time, so they are mostly used for protection functions. Digital types, on the other hand, come with interfaces like I2C, SM bus, and PM bus, and are mainly used for monitoring and optimizing the system. Their response time is slower. So, their response time is relatively slower compared to analog types. So, in summary, analog types are mainly used for protection mechanisms, while digital types are used for monitoring and optimizing system performance. Currently, we have 4 types of current sense. The most common type is the voltage type. For example, Richtech has products like the RTQ6060 and RTQ6058, which have analog voltage. For digital types, used for monitoring and optimizing the system, Richtech offers the RTQ6053, RTQ6056, and RTQ6059, with I2C interfaces for reporting and optimizing the system. Next, we have products with alert functions. The alert function is available in Richtech products like the RTQ6060 and RTQ6052. Some systems require faster response times, so we include a comparator that can sense and output directly with an open drain output for faster system response in system applications. Currently, there are fewer customers using them, but Richtech will still develop products for this market. If you have any particular specifications and requirements, please contact the Richtech branch office close to you. We will see how we can work with you and move forward with development. If you have needs, please contact Richtech for specifications and development. We will discuss the details. Currently, current sense amplifiers can be divided into two types: single unidirectional and bidirectional. For digital types with I2C, most are bidirectional. For analog types, a simple way to determine: you can simply check if the IC has a V reference pin. If it has a V reference pin, it is bidirectional, because it compares V out to determine the direction of current. So basically, if you see a V reference pin, it is bidirectional. Currently, bidirectional types are mostly used in battery-related applications or motor-related applications, but many applications still primarily use single-directional types. Next, current sense amplifiers can be applied in both high side and low side. Each option has its own advantages and disadvantages. Currently, most applications use high side placement because high side placement allows for short circuit detection to detect shorts. Of course, in this case, you need to choose a common mode with a high voltage common pin. The common mode pin needs to withstand high voltage. Of course, if placed on the low side, you don't need to consider high voltage, as it doesn't need to withstand high voltage. You might lose some short-circuit detection protection mechanisms. Alright, next we will introduce some key items of current sense to everyone. As you can see, here shows the gain. These are the main parameters of current sense that we need to pay special attention to when looking at current sense specifications. These parameters are basically related to the overall system error. Here is an example. Currently, you can see that we are using the RTQ6052 current sense as an example. Here you can see that we currently have common mode and differential mode voltage ratings. So basically, the voltage rating that your IC needs to detect is determined by your common mode. For the voltage difference, you can look at the differential mode to see the voltage rating range. Next, we have the error items. Here, we directly list the specifications for your convenience, so you can see the corresponding values. Next, we will introduce each parameter and explain their meanings, as well as how to select and calculate them. When discussing error values, we need to first understand how to select the appropriate current sense for your application and its output range. Here is an example. Assume my VCC is 12 volts for power supply. You can see that for the RTQ6052. If you select a gain of 100, then the output range will be VCC minus 0.15 volts, which is the output range. As you can see in the diagram, it's 11.85 volts. A minimum value is around 100 millivolts, which is approximately 0.15 volts. So basically, this is the basic output range it can cover. In the industry standard, typically, we consider an 80% tolerance to account for other tolerances. So usually, 80% is relatively safe, Within this range, you can see that the output range is recommended to be between 2 volts and 10 volts. In design, it's preferable to keep it within this range to ensure it is relatively safe and reliable. Of course, from the output, you can back calculate to determine the resistor value and the corresponding current value. Next, regarding the error part, the error mentioned earlier is the sum of all the parameters. This includes offset error and gain error. We will introduce offset in detail later, including offset error, CMRR, and PSRR errors, and how to calculate them. The total error also includes gain error. All the IC errors are summed up to get the total error. Usually, most customers rarely sum them up to get the total error, because in practice, it is relatively more realistic and practical. In real life, it is less likely to happen, unless you are in military-related industries where such precision is required. In industrial or consumer-grade applications, for industrial and consumer grades, statistically speaking, we usually calculate using the root mean square method. So basically, the total error is calculated by taking these different parameters and using the root mean square to get your total error. Next, let's start looking at each parameter one by one. For offset error, I will provide an example to make it easier to understand for everyone. As you can see, the offset specification is 2.5 millivolts. Assume my gain is set to 20. If the input offset is around 2.5 millivolts, then correspondingly, we can calculate that if the expected sense output is expected to be 2 volts, with an offset of 2.5 millivolts multiplied by the gain, we will have an error of 0.05 volts. This 0.05 volts error divided by the gain multiplied by the output, multiplied by the input sense voltage. So 0.05 volts divided by 2 volts gives us the offset error 2.5%, which is 0.05 volts divided by 2 volts. So the offset error is 2.5%. Next, after offset, we need to calculate the PSRR error. According to the specifications, we use 12 volts for PSRR at the input side with VCC supplied at 12 volts. It means when your supply voltage is not 12 volts, for example, 15 volts, there will be an error. So basically, this will generate a PSRR error. Correspondingly, this specification is the slope of the PSRR within this voltage range. So basically, we directly calculate it as 20 amps multiplied by 1 milliohm. This is basically an ideal sense voltage. Correspondingly, the numerator is the voltage difference at the input. This means that if my specification is 12 volts, and if you are using 12 volts as well, then basically my error is 0. If your supply voltage is 15 volts, then you have a voltage difference of 3 volts compared to our defined value. Then multiply this by the slope, which is 100 microvolts. You will get a 1.5% error. How to improve this error? Of course, you can start by adjusting the denominator. The denominator here is the sense resistor and current. The only thing you can change is to increase the sense resistor. This will reduce the error value. Otherwise, the first option would be to choose another suitable CSOP product to reduce your error value. A CMRR error is very similar in concept to PSRR, but we calculate the input voltage. We also use 12 volts as the reference. The CMRR value here is expressed in dB, so we need to convert it to a slope similar to the PSRR. So basically, here we use 20 log, which calculates to 10 to the power of -4. We take 80 volts as the worst-case scenario. For 80 dB, the worst-case scenario with 10 to the power of -4, which is approximately 100 microvolts. So currently, the denominator is still the ideal sense voltage. Here, similarly, the voltage difference detected at the input side is 12 volts minus 5 volts. Assuming 5 volts is detected, subtracting this and then multiplying by the CMRR slope, multiplying by the CMRR slope, and then multiplying by 100% will give you the error value. This error is the same as the PSRR. You can either increase your sense resistor, or you may need to choose another suitable current sense component to meet your design specifications. So, what we just discussed was the offset error. Next, we will talk about the gain error. For the gain error, we take an average gain value, which is relatively linear, as an average value which is relatively linear. Because it has a linear characteristic, you can see in the specifications that it already has a fixed value, which is around plus or minus 1%. As you can see, this is plus or minus 1%. For the nonlinearity part, basically, because it still has linear characteristic, the gain error is taken as an average value. If you look at it on a smaller scale, in each small segment, there are still some fluctuations. For the maximum value of these fluctuations, when we calculate this range, we can basically obtain the nonlinearity error values. As I mentioned earlier, all the errors, including offset error and gain error, when added together, give us the total error. So this is all about the calculations for all the CSOP errors.